A new crystalline form of water ice has been discovered in fleeting transitions between phases at high pressures. It's called Ice-VII, and it takes place as the substance slides between two already known, cubic arrangements of molecules. Although it's unlikely Ice-VII would naturally appear on Earth's surface, it could reveal more about how water behaves on massive alien worlds. We might think it commonplace, but water is actually pretty weird compared to other liquids we know. The arrangement of molecules within water's frozen form, ice, can vary significantly, depending on the conditions around it. We know of at least 19 of these solid phases of ice, some of which occur naturally, some of which have only been seen in laboratory conditions. The ice you see in the freezer, or falling from the sky as snowflakes or hailstones, is the most common natural ice on Earth. It is called Ice-VII, with oxygen atoms arranged in a hexagonal grid. The structure is, however, geometrically frustrated, with the hydrogen atoms hanging about in a disorderly fashion. When physicists cool Ice-VII at various temperatures and apply different pressures to it, the hydrogen and oxygen atoms within can periodically reach different arrangements, sometimes even ordering themselves more neatly. These various forms of water ice are not always stable, but we can explore these in the lab to reveal their curious molecular structures. Two of these phases that have cubic structures are Ice-VII, which has disordered hydrogen, and Ice-VI, which is symmetric. These can be reached by subjecting ice to high pressures, tens to hundreds of thousands greater than Earth's atmospheric pressure, at sea level, Ice-VII at even lower pressures than Ice-VI. To study the transitions between ice phases, a team of physicists led by Zach Grande of the University of Nevada, Las Vegas performed experiments on high-pressure ice using a new technique to measure the properties of the ice as pressure was applied. The researchers squeezed a sample of water in a diamond anvil, forcing it to freeze in a jumble of crystals. Lasers were used to then heat the sample, causing it to melt before refreezing into what the researchers described as a powder-like collection of crystals. By incrementally raising the pressure in the anvil, with periodic blasts from the laser, the researchers created Ice-VII and observed the transition to Ice-VI. In between, thanks to their new measurement technique, they also observed the new intermediate phase, Ice-VIIT. In this phase, the cubic lattice of Ice-VII is stretched along one of its vectors so that the structure extends into a rectangular arrangement, with a cubic footprint, before settling into the symmetric, fully ordered cubic arrangement of Ice-VI. This arrangement is known as Tetragonal. The team also showed that Ice-VI can form at much lower pressures than previously thought. Ice-VII forms from approximately 3 gigapascals, that is, 30,000 atmospheric pressures. According to the team's observations, the transition to Ice-VII occurs at around 5.1 gigapascals. Previous reports have put the transition pressure for Ice-VI between 40 and 120 gigapascals. However, Grande and his team observed the transition between Ice-VIIT and Ice-VI occurring at around 30.9 gigapascals. This, the team said, should help resolve the debate about the Ice-VI transition pressure. Zach's work has demonstrated that this transformation to an ionic state occurs at much lower pressures than ever thought before, said physicist Ashkan Salamat of the University of Nevada, Las Vegas. It's the missing piece, and the most precise measurements ever on water at these conditions. This, the team said, could have important implications for studying the interior conditions of other worlds. Water-rich planets outside the solar system could, they said, have Ice-VIIT in abundance, even increasing the chance of conditions suitable for the emergence of life. The team's research has been Physical Review B.